In this video, we're going to be looking at Graham's law, focusing on effusion problems, right? So we're going to be working example problems applying Graham's law to situations involving effusion. So here's an example problem. Hydrogen in a stainless steel container at 5 atmospheres leaks out of a pinhole at a rate of 0.0100 atmospheres per minute. At what rate would methane, under the same conditions, leak from the container? Now, one thing to notice here is the units of the rate. All right, remember, the form of the law is that rate 1 divided by rate 2 equals the square root of the molar mass of 2 divided by the square root of the molar mass of 1. Now, since we have rates together here in a ratio, the units of the rate don't matter as long as they're valid units. Right? So here we have an amount and a time. That's a rate. So whatever the rate units of one rate will be the units of the other. And so Graham's law is very flexible in terms of what kinds of units you use for the rate. Okay, so given our information here, we've got hydrogen gas, which is diatomic, and the molar mass is 2.016 grams per mole. Methane has a molar mass of 16.04 grams per mole. And the other flexible thing is it doesn't matter which we pick as participant 1 and which one we do as 2. As I've worked this problem, I arbitrarily chose hydrogen as 1 and methane as 2. But again, it wouldn't matter. Right? So given that, the rate at which hydrogen escapes is rate 1, so we have 0.0100 atmospheres per minute divided by the rate at which methane escapes is equal to the square root of the molar mass of methane, which is 16.04 grams per mole, divided by the square root of the molar mass of hydrogen, which is 2.016 grams per mole. But we know that mathematically those can be combined into 16.04 grams per mole divided by 2.016 grams per mole with the square root of the whole fraction, right? Which is equal to the square root of 7.95, and I'm going to add some extra significant figures here, or some extra figures beyond what's significant. And note there would be no units there, right? Because our units of the numerator and denominator are the same, so we have no units there. And then when we do the square root, we get 2.8207. Again, keeping some extra digits beyond what is significant so that we don't contribute to the rounding error. So, coming off the last page, we have 0.0100 atmospheres per minute. That's the rate of effusion of the hydrogen gas, divided by the unknown rate of effusion of the methane gas, is equal to 2.807. So if we multiply through by the rate of methane effusion, we get that 0.100 atmosphere per minute equals 2.807 times the rate at which methane effuses. Right? If we get that now and divide both sides by the 2.807, right? In order to eliminate that from the right side, we get, right, when we do this math, the point, oh, made a math error there. Let's fix that. Right, we have to be careful. Right, it's 0.0100 atmospheres per minute. Right, we always have to be watching to make sure we've properly transcribed our numbers. Right, so if we take that divided by the 2.807, you end up with 3.55 times 10 to the minus 3 atmospheres per minute equals the rate at which methane is effusing from the container under the same conditions. Right? So there is an example of using one rate to find the rate of another gas effusing from the same container. Here's another problem, right? The rate of effusion of an unknown gas was found to be 24 milliliters per minute. Again, a different expression of rate, but still valid because of the form of the Graham's law equation. If methane gas, CH4, under the same conditions, effuses at a rate of 48.7 milliliters per minute, what is the molecular weight of the unknown gas? Right? So what we know is we have an unknown gas, and its rate is 24 milliliters per minute. And we have methane gas, and its rate is 48.7 milliliters per minute. Okay? So, we know the molar mass of methane, right? We used that in our previous problem, is 16.04 grams per mole. We don't know the molar mass of the unknown gas, right? That is our unknown. But we know the rate at which methane escapes. That is 48.7 milliliters per minute. And we also know the rate at which the unknown gas escapes. It is 24 milliliters per minute. Okay? So again, it is an arbitrary choice, but I'm going to make, right, methane our number 1 and the unknown gas the number 2 in setting up our Graham's law of effusion. Right? So we've got, right, rate 1 divided by rate 2 equals the square root of the molar mass of 2 divided by the square root of the molar mass of 1. Right? Again, right, the 1s are across from each other, the 2s are across from each other. And so now we substitute. Right, 1 is the methane, so rate 1 is the 48.7 milliliters per minute divided by rate 2, that's the rate of the unknown, 24.0 milliliters per minute. That's going to be equal to the square root of the molar mass of the unknown, because that's 2, and we don't know that, divided by the square root of the molar mass of methane, which is 16.04 grams per mole. Okay, so there is the setup of our expression. So if we multiply both sides of our expression by the square root of the molar mass of methane, we can isolate the molar mass, the square root of the molar mass of our unknown. And so we would get our 48.7 milliliters per minute times the square root of 16.04 grams per mole divided by 24.0 milliliters per minute, and that's going to equal to the square root of the molar mass of our unknown gas. So if we bring that same expression to a new page where we've got some room to work, right, we can take the square root of this, right? We have to take that square root first in terms of order of operations. And so we can get 48.7 milliliters per minute times 4.005 grams per mole to the 1/2, right? Just the unit is raised to the 1/2. We took the square root of that, divided by the 24.0 milliliters per minute, and that equals the square root of the molar mass of the unknown. Now, if we do this math, this times this divided by this, we will get an expression that looks like this. That 8.1268 times grams per mole to the 1/2, right? That's our unit, is equal to the square root of the molar mass of the unknown, right? Because the milliliters per minute unit divides out, becomes 1, leaving us only with the square root of grams per mole as our unit. Now, since this is a square root, one of the things that we can do then is to get rid of the square root, we square the whole thing, which means we square that whole thing. So if you square this 8.1268, what you get is that 66.0 grams per mole is the molar mass of the unknown, right? And so that is the molar mass of the unknown. Here's our third and final problem, okay? So, it took 5 minutes for 1 liter of neon gas to effuse, this should be effuse, through a porous barrier. How long will it take krypton under the same conditions to effuse through the barrier? Okay? So, right, with neon gas, what do we know? Right, well, we've got, right, for neon, we've got the molar mass of neon, and that molar mass of neon would be 20.18 grams per mole. Now, what they haven't really given us is directly a rate at which neon is escaping. But again, we can use anything that is changing with time to develop a rate. So our rate at which neon is effusing is at 1 liter per 5 minutes. And so that becomes our rate. 0.20 liters per minute is the rate at which neon is escaping. Now, the only thing we know about the krypton is that its molar mass is 83.80 grams per mole, right? Didn't plan that out. And what we're trying to find is the rate at which krypton is escaping, right? So again, the choice is arbitrary, but I'm going to use, right, neon as 1, krypton as 2 in our Graham's law expression, right? So we've got the rate of 1 divided by the rate of 2 equals the square root of the molar mass of 2 divided by the square root of the molar mass of 1. And now we substitute. Right? So 1 is neon, so its rate is 0.20 liters per minute. Right? What we don't know is the rate at which krypton escapes, but we know that the square root of, right, the molar mass of krypton is 83.80 grams per mole. We'll take the square root of that. That the molar mass of neon is 20.18 grams per mole, and we'll take the square root of that. Right? So our 0.20 liters per minute divided by the unknown rate at which krypton escapes would be equal to the square root, we could combine that, of 83.80 grams per mole divided by 20.18 grams per mole. Right? We get that square root equals the square root of 4.1526, which equals 2.038. So again, we'll transfer this to a new page where we have room to work. Right? So if we multiply both sides by the rate of krypton to get it out of the denominator, we get our 0.20 liters per minute equals 2.038 times the rate at which krypton escapes. Right? If we divide both sides by 2.038, right, that eliminates that on that side, leaving only the rate at which krypton escapes. And so we end up then with 0.0981 liters per minute, being equal to the rate at which krypton escapes. Okay? Now that's the rate, but the question was, right, if we go back to the question was how long? Which suggests we want our answer to be in units of time. Okay? Well, if you remember, we expressed our rate at which neon escaped initially as 1.0 liter in 5 minutes. And so how long, we could express it as how long for 1 liter of krypton to escape. Right? That would be consistent with a question that wants time as the answer, right? To make it consistent, we will allow the same amount of krypton to escape as neon escaped. Right? So we know the rate at which krypton escapes is 0.0981 liters per minute. We know we want to know how many minutes are equivalent to 1 liter escaping. Well, we can use this as a relationship like we did in unit conversions, right? That's the equivalent of saying 0.0981 liters escaping equals 1 minute of time. So we can use that, put our 1 minute on top, divide it by 0.0981 liters. Liters cancels, leaving us a time unit, and we get 10.2 minutes for 1 liter of krypton to escape. So there's 3 examples of ways we can use Graham's law of effusion in problems.